Okay, so we'll go back to another video. So here we have a trigonometric integral where if we look at the integrand, it looks very similar to a Gaussian lookalike integral. So of course we know the Gaussian integral is over the half real line or the entire real line of e to the negative x squared. But here we have a different input. Instead, it's negative tangent square x. So would this mean that this will be similar to evaluating the Gaussian integral the way it should be in this similar situation? Not exactly. So what we'll do here is, of course, the first step to give away is we're actually going to perform a nice little u-sub, converting this into a different integral. From there, we're actually going to define a different integral such that when we plug in a specific value to that different integral, it's actually evaluating what our given is supposed to be. So expect a bunch of differential equations that's actually going to come into handy, and special functions. Really, the error function is going to be very nice. And we're actually going to be evaluating a special type of antiderivative where in that situation, you think it's not that easily can be integrated to get some sort of elementary function, but we can actually take this into another approach to actually get what we need to do from there. So with that, let's actually just jump right in. So let's call this capital I. Well, let me first do our u sub. We're going to let u equals tangent of x. Then that means du is equal to secant square of x dx. Now, of course, we have to get dx by itself to make things a little bit simpler. So divide the secant square x from both sides. So I have du divided by secant square x. But that won't work since we have a u and an x together, which won't work. So we have to get everything in terms of u. But notice that secant square of x is actually the same thing written as 1 plus tangent square x. And what's great is that we have a u equals tangent x. So therefore, to put this simply, we have that du is du divided by 1 plus u square is equal to dx. Okay, and so with that, now call capital I our given integral. Now we change our bounds. So we have pi over 2 and then tangent of pi over 2, that's going to approach positive infinity. Meanwhile, by plugging 0, then that means that's going to be 0. So now we'll have e to the negative u square and then divided by 1 plus u square and then du. Now with this in mind, now let's actually define the integral that we're going to use. Then with that, we're actually going to plug in that special value such that it's actually going to give us the integral that we want to evaluate for. So let's actually call this function, so capital I sub I of a. So we'll call this is the integral from 0 to infinity of e to the negative a square u square and then divided by 1 plus u square and then du. Okay, so here's some things we want to notice. So I'm going to put this on the top over here. If I plug in a for 1, so I sub 1, if I plug 1 into here, we're actually going to get exactly what this is. So it's equal to I, so let me put this on the side and say, want to evaluate. So another thing we'll do is suppose that I did mention there's going to be some differential equations involved. So we know that when we're solving for the unknown variables and sort of thing, we can always plug in the guess and check of a base solution. So now let us consider that I sub 0. So if I plug 0 into here, then that means e to the power 0 squared. So that means that's just going to be 1 on the numerator. So if I put this back together, I have the integral from 0 to infinity of 1 divided by 1 plus u squared. And we know that that's the antiderivative of that is arctangent of u. Plug in the bound, so that means that's actually going to yield us with pi divided by 2. With everything in mind, let me actually just box this of our information that we have, that we observed for, that we actually want to keep this in mind. Well, of course, this is what we want to evaluate, but meanwhile, I have I sub 0 is equal to pi divided by 2. So that's actually something to keep in mind of in the back of your head once it's come in handy. Okay, so with this, I'm actually going to use the same marker for that. Next thing we'll do is let's actually perform some Feynman's technique and differentiate inside of the integral. So I have capital I prime of a is going to equal to, so 0 to infinity. Then if I differentiate in respect to a over here, so what we'll have is we're going to get negative 2a then times u squared multiplied with e to negative a squared u squared and then divided by 1 plus u squared then du. So what we'll do here is we're actually going to break this up a bit. Now note that I'll also factor out a negative 2a outside of the integral as well. So let me actually put that in mind. So continuing forward, this is what we have. What I'm going to do is I'm actually going to break up this u squared such that I'm going to add and subtract 1. So doing so will actually allows us to perform the linearity we will want to do to make evaluating this a little bit easier. So now I have negative 2a multiplied with the integral from 0 to infinity. So inside we break this up, I have u squared plus 1 and then subtract 1 and then multiply with e to the negative a squared u squared, then divide by 1 plus u squared du. Then simply moving forward that we can break this up. So now we have that the u squared plus 1 or 1 plus u squared, same thing. So that will cancel out, distribute that back here. So that's a 1. So now we have negative 2a multiplied with the integral from 0 to infinity of e to the power negative a squared u squared du. And then add this with 2a, then multiply with the integral from 0 to infinity of the same thing of the numerator. And then afterwards, we divide this by 1 plus u squared and then du. Notice that if we take a look at our integral over here, that's the exact same thing as I sub I of a. So I can actually just replace that. And it's actually, we're dealing with more functions coming up. So now going back to here. So now to simply put this back over here, I'm going to continue forward with this arrow denoting here. So far what we have is that this is going to be I prime of a. And then with this in mind, I'm actually going to subtract. So I have subtract 2a and then I of a, which is then equal to negative 2a times the integral from 0 to infinity of e to the negative u squared, or rather I write this as a squared, then u squared, and then du. Okay. So far, so good. Now, how do we tackle such integrals as this? Since we want to get things out of the way in order to get into the world of differential equations, make things a little easier. So this is actually not so bad. So let me actually put a little asterisk over here. This integral, so 0 to infinity of e to the negative a squared u squared du. Now, let me switch a marker for this one. So evaluating this specific integral, suppose that now we can actually just do a little u sub. So we'll let u, or I'll call this different variable. We're going to call this t. We'll let t equals a times u. Then if I differentiate, I have dt divided by, or dt is equal to a times du. Then I'll divide the a to both sides. Okay, and so I also forgot to write the negative 2a, so I'll just write this in the next step. So now we have that 2a, then multiply with the integral. So we want to change our bounds, but no worries, because it's not going to do anything any different. So it's still going to be the same. So it's negative 2a times the integral from 0 to infinity. Then replace this, we have e, and then negative t squared. And then replace this with our new du differential, just divide the a. So we have dt divided by a, which of course that the a, I factor that out, and then that'll cancel outside. So then I have negative 2 multiplied with the integral from 0 to infinity of e to the negative t squared dt. Guess what? That's actually in the form of the Gaussian integral. And so we know that that's the well-known value of square root of pi divided by 2. Then the 2's will cancel. And so we're just left with negative square root of pi. So now this entire thing over here changes to I prime of a. We have the following equation, so minus 2ai of a, which is then just equal to negative square root of pi. So that actually deduces everything to make things a little bit easier and simpler. So take a look at this. It is in the form of a differential equation. What is this? This is known as the first order linear equation. So what this means, to tackle such equation, we actually need to find an integrating factor and then multiply to this entire thing. Then we'll notice that that's actually going backwards when it comes to the implicit differentiation of the product rule. And so with this, so now let's call our integrating factor, move a, and that's how the standard naming convention is. So we take what's in front of I sub a, so that's negative 2a, so it's written as e, then to the power, the integral of negative 2a dA, and of course, that's actually just gonna come down to negative e to the power negative a squared. Okay, so with this, now I just multiplied this to both sides of everything. So over here, that means I have e, then negative a squared, multiply I prime of a. Then next I have, this is minus 2a, then e to the negative a squared, I sub a. Then set this equal to negative square root of pi, then e to the power negative a squared. Okay, and then if we undo this, then we know that this is actually just taking the derivative of in form of the product rule. So this means this is the derivative in respect to a of e to the negative a squared, and then times I of a. Okay, and then set this equal to, this is still the same thing, negative square root of pi divided or multiplied with e to the negative a squared. Okay, so we can undo all this by actually now just integrating both sides in respect to a. So integrate here and then here. So that means that just undoes that. So we have e to the negative a squared times I of a, and then set this equal to, so I'll just factor out the negative square root of pi. And so far, this is the interesting part. We have now the indefinite integral of e to the negative a squared dA. So of course, with the Gaussian function, there is that bound, but here we don't have a bound. So what do we do from here? Because we know that it's well known that it's kind of difficult to find an elementary function when we're, finding its own antiderivative of that Gaussian function. So here's the interesting thing with our integrand over here. So pay attention with our series that we'll be using to perform this expansion over here. So e to the negative a squared has the following expansion with the Maclaurin series, of course, at a is equal to 0 of the infinite sum at n is equal 0 of negative 1 to the power n, then times x to the power 2n, and then divided by n factorial. And so with this in mind, now what we'll do here is let's actually integrate both sides in respect to a. So I guess this is good room here. So e negative a squared dA, set this equal to, so the integral of the infinite sum of the entire thing over here. And so what's great is that this series actually converges absolutely, so I can actually just interchange the sum and integral. And if we perform all this out, so that means now the sum becomes the following. So we have now the infinite sum, n is equal 0 of negative 1 to the power n, then multiply with x to the power 2n plus 1 divided by 2n plus 1, and then multiply with n factorial. And of course, it's a definite integral, so make sure to add the c. Your unknown constant is always important. Okay, and so what's great is that the error function has that very similar representation of the infinite series. So that's written as 2 divided by the square root of pi, and then multiply with the infinite sum at n is equal 0 of actually just the same thing over here. So negative 1 to the power n, then x to the power 2n plus 1, and then divided by 2n plus 1, and then multiply with n factorial. So with this, I could actually just replace here, and so that's the same thing written as the square root of pi divided by 2, multiplied with the error function at a. That's supposed to be an a, by the way. I apologize for that. Everything for the x is supposed to be a. So after I write this down, let me actually give me a second to change this. So square root of pi divided by 2, and then error function a, and then add this with c. So that's actually the series representation over here, which is actually equivalent to the indefinite integral e to negative a squared is equivalent to this following over here. So now we're pretty much almost getting there. So I sub a, and then if I just divide the e to the negative a squared to both sides of the equation, we already have that. So all that comes down to now is that we have negative is equal to negative square root of pi, then times e to the power a squared, and then substitute for the indefinite integral over here with over here. So multiply with the square root of pi divided by 2 times the error function of a, and then add this with c times e to the power a squared. Okay. And this is really important that we have to find that constant, which is why we said from earlier that I sub 0, we just used the easier case. I sub 0 is equal to pi divided by 2. So if I just plug 0 over here, that means the whole thing has to be set to pi divided by 2. If I plug a for 0, so that means this is actually just going to be, so the square root of pi. Well, it doesn't matter because the error function of 0 is going to be 0, so that gets rid of itself. And then e to the 0 squared, that's just going to be 1. And so therefore, we now have that c is just equal to pi divided by 2. Okay, so with that in mind, let's actually just continue forward. So I of a is then equal to, so simplify some things out that square roots we're going to cancel. So we'll have now, this is just negative pi divided by 2, multiply with e to the a squared, multiply the error function of a, and then add this with pi divided by 2, multiply with e to the power a squared. Okay, so now the last thing to do is I sub 1 we want to evaluate, which is our given. So now just plug in 1, so that means error function of 1, that's just by itself. Then e to the 1 squared is just e, so pi e, then divided by 2. But I can also factor that out. So I have pi times e divided by 2, and then multiply with 1, and then subtract the error function evaluated at 1. And so therefore, that actually completes the final evaluation of our given integral, the Gaussian lookalike in a trigonometric sense. So there we have it. All this out with all the differential equations put out together, starting with the u substitution, and then getting everything in nice simplification, and there we have it. So yeah, That's pretty cool if you ask me.